What's up, guys? How are you? Now, today we're talking about acids and bases. You've heard of acids before. These are, the dangerous acids in your car batteries and, other dangerous stuff. So, you've heard of acids, but we need to define acids chemically, and I need to tell you when it comes to chemistry, what do we call an acid and what do we call a base and how are they different. So that's what I'm going to be defining today, and we'll do a few exercises about how to tell the difference between acids and bases. All right, let's jump into it. So acids and bases. What is an acid and how is it different from a base? So usually you hear acid as something that tastes sour or something dangerous that can dissolve metals or they can dissolve your skin. Bases are things that taste bitter, they can be slippery, they can be corrosive, but that's not enough. We need to really define what a acid and base is. So there have been two theories that help us understand in chemistry what an acid and base is, and we started with Arrhenius. Now, Arrhenius told us that an acid is something that, when dissolved in water, produces hydrogen ions. And we also call hydrogen ions protons. Now, why do we call hydrogen ions protons? Well, remember that hydrogen has an electron and a proton, right? Well, when the hydrogen atom loses an electron and becomes an ion H plus, what does it have now? It doesn't have any electrons. It only has one proton, right? And what do we call that? It's just one proton. So an H plus ion has one proton and we call it a proton. So an acid is something that can lose a proton when dissolved in water. So HCl is an example of an acid that gives you H plus plus Cl minus. Now let me give you a general representation of an acid. Is HA gives YH plus plus Cl minus, not Cl minus, but A minus, because it's A, right? A minus. There you go. All right. What about a base? According to Arrhenius, he said that a base is something that loses all H ions, hydroxide ions, when dissolved in water. So instead of losing H plus ions, it loses hydroxide ions. So NaOH gives you Na plus plus OH minus. This is a base according to Arrhenius. So a general representation is like BOH. B is a base, right? BOH will give you B plus plus OH minus, right? This is an example of a base according to Arrhenius. So a problem comes where there are things in nature that behave like bases, but they don't fit this description. So science in general had to come up with a new definition of acids and bases. So this is where these two guys come in, Bronsted and Rory. So Bronsted and Rory simplified things. They say that an acid is a proton donor. An acid is something that gives away a proton. It's the same as Arrhenius, right? So an acid, it will be Ha, something that gives away H plus, which is a proton, plus A minus, right? This is according to Bronsted and Rory. But a base is no longer an OH donor. Rather, it's a proton acceptor. This is really important. Anything that accepts protons, anything that accepts H plus ions is considered a base. It doesn't matter if it has OH or not. And these define the base to include a lot of other chemicals, right? So a base will be represented now by base plus H plus will give you BH plus, right? A base is something that gets a proton, right? So now let me show you something. We just say that these things happen in water. So we have another way to represent this in water, to represent a base and an acid in water. So when these two things are in water, they are going to behave this way. So HA in water, so HA plus H2O is going to give you, so HA will give H plus, it gives away H plus, but H plus is not going to be by itself. It's going to go and join water. So it's going to be H3O plus because it has joined water, and then you have your A minus here. So this is how this equation is represented when we add water. How about this one? You have a B plus H2O. And look at this. Because B is a base, B is a proton acceptor. So it will accept a proton. Where will the proton come from? From the water. So it's going to be BH plus what? Plus OH minus that's left in water, right? So this is really important because this is how these will react in water. And it's important because it shows a very important quality of water. What is it? Water here gained a proton. Water here gained a proton from an acid. What's the thing that gains a proton? It's a base, right? So let's just say B here. What about here? Water gave a proton to the base. So water gave hydrogen to the base. So it's acting as an acid because acid is a what? It's a proton donor. So when you have a base in water, water is going to act as an acid. When you have an acid in water, water is going to act as a base, right? And we'll talk more about the qualities of water, but let's look at examples of this. So HCl, for example, HCl is an acid. When it's in water, water acts as a base. And water is going to take the H plus from HCl to become H3O plus and Cl minus, right? And then a base, again, according to Bronsted and Rowley, a base is a proton acceptor. So NH3 is an example of a base, and it's going to accept a proton from H2O. So it's going to become NH4 plus, and then OH will be left here. So here the water acted as an acid. Here it acts as a base, right? So these two really, you really need to know them because they are representations of acids and bases in water. All right. So the water is very special, as in it acts as an acid and base, and we call this quality amphiprotic, right? It's an amphiprotic, which is something that behaves just like an acid and a base, and water is one of the best, and it's one of the reasons why water is involved in a lot of things. And you know, it's the most universal solvent because it can dissolve acids and can dissolve bases. And we also know other reasons why, you know, the water is a really good solvent, such as forms hydrogen bonds, its polarity, and so on and so forth. But that should give you an idea of what a base and an acid is and the differences between them. Now let's talk about the difference between a weak acid and a strong acid. And what about bases? What's the difference between weak bases and strong bases? Well, when it comes to the strength, the way you have to think about it is the dissociation. We talked about how these all get into the water and they dissociate, right? So it's the degree of dissociation. If something dissociates completely, it's a strong electrolyte. If something doesn't dissociate, it's a weak electrolyte, right? So strong acids and bases react completely in water. So we talked about, let me show you, let's go back to how we represented acids. We say that acids are HA, right? And they give away their proton like this. Well, these, if it's a strong acid, all of HA will be turned into H plus A minus, all of it. So it dissolves completely, right? But a weak acid, right? So let's have HA turn into H plus A minus. It won't dissolve completely. It will be a reversible reaction. So as you make H plus A minus, this will be making HA. That means that HA will never completely dissolve. That's a weak acid. So this is the difference between a weak acid. This side is strong. So you have a strong acid here and then a weak acid here. All right, so check this out. We say that this dissolves completely. This one dissolves partially. This might just say partially. And then this one is irreversible. This one is reversible. Okay. Another big difference is we write this down with one arrow. We write this down with two arrows. That's how we show that one is reversible, the other one is irreversible. Here you have no equilibrium because there is no reversible reaction. Here you have equilibrium. All right, so that's the difference between a strong acid and a weak acid. It's the same with the strong base and a weak base. The only difference is that we're just going to have a base instead of an acid. So there are some examples of strong acids and bases here. So I tell students to really remember the strong acids and strong bases because it's a shorter list. It's a much shorter list. So these are the most common strong acids. And you have HBr, HCl, HI, nitric acid, and all of these. But usually, HCl is one of the model acid that we use. Right? We use HCl a lot as an example. Here for weak acid, we use acetic acid as an example. And again, remember these are acids, so they are just going to lose the hydrogen. All right, now for the bases, hydroxides, as you can see, hydroxides will be the strong acids. Hydroxides are strong acid. Ammonia is a famous example of a weak base. So these four are the most used as examples. So HCl is a strong acid. NaOH is a strong base. Acetic acid is a weak acid. Ammonia or NH3 is a weak base. These are the model examples, but of course there are a lot of variations. All right, so let me show you examples of how weak acids behave in water. So for example, acetic acid, you add H2O, and what's going to happen? It's going to give this H to H2O. So you get H3O, and then you have CH3COO negative. A lot of students get confused on what to do, but all you have to remember is the general behavior of how an acid behaves, right? So the general behavior is HA gives you H plus plus A minus. So here, COOH, pretty much this whole group is A. So here you have HA, right? It's HA, and then this group here is A minus, right? But we still do them the same way. Weak bases, same idea, right? Take a weak base, you add a water, is the other way. Instead of getting water, giving water, right? Instead of getting water, instead of H plus being given to water, here H plus will be taken from water because this is a base. The base receives H plus. So it's going to be an H4 plus OH minus, right? So this is how you know. So make sure that you know how to show me how a strong acid. So if you're given a compound, you should be able to know whether it's an acid or a base. And then after that, you should know whether it's a strong or weak acid or base. And then after that, you should be able to write down how it behaves in water. And again, these are the things that we looked at earlier, where this is, this up here is how they behave in water. If it's a strong acid or base, you're going to have one arrow. If it's a weak acid or base, you're going to have two arrows to show that it is reversible. But that is how you tell the difference between a weak and strong acid and bases. Right? So some examples here. No, not this one. This one, right? So say write the chemical reaction of the following acids and bases in water. So let's just look at a few of them. HF, which is a weak acid, they told us what it is. So HF, how does it react in water, right? They told us it's a weak acid. Weak acid. So first of all, the fact that it's an acid is going to give its H plus to water, and then it's weak, so it's going to be reversible. So two arrows. It's going to give us H3O plus HF minus, right? Very easy. H2S, weak acid. Weak acid, so it's H2S plus H2O, and it's a weak acid, so it's going to give away its H plus. I don't know why I said H2O. This is H2S. All right. H2S. All right, so notice something different on this one. H2S is different because it has two hydrogens. So H2S has two hydrogens. So what happens to water? What happens to the reaction? What, I wrote H2O again? Wow. H2S. All right. So okay, it doesn't really want to be there. H2S. There you go. All right, so H2S has two hydrogens. What happens? Well, you're going to need two waters. That's what it is. If one hydrogen reacts to one water, like above here, if you have two hydrogens, you're going to need two waters. So 2H2O. It's that easy. And then in the end, guess what you get? You get 2H3O plus S2 minus, right? And it's a weak acid, so you get the arrow. It's that easy. What about a strong acid? HNO3 3 is a strong acid, but it's an acid. So when you add it to water, it's going to give you, so you have one arrow because it's a strong acid, and then it's going to give away its hydrogen to water. So it's H3O plus NO3 minus. All right. Last one, we have a weak base. So this one is a base. So in water, bases get the hydrogen from water, right? So in H2O, this is going to get the hydrogen from water. Where does the hydrogen go? It joins these other hydrogens at the end, just like nitrogen. So this is going to be CH3NH3 plus what? Plus OH minus that's left on water. So that's how you give that's how you pretty much figure out how an acid or a base, whether weak or strong, is going to act in water. All right, so let's talk about the acid and base dissociation. And actually, first let's talk about when you have an acid and base react together, right? Something. So let's go back here actually. Let's say you have an acid and a base. Acid plus a base. If you have an acid plus a base, acid will give the hydrogen, because acid is something that gives away hydrogen. Acid will give the hydrogen to a base. So you have A minus plus HB. All right. So something interesting happens when you do that. HA is something that gives away hydrogen. It's an acid. But if it's already given away hydrogen, it's going to now need hydrogen. So this A minus right here is something that needs hydrogen. It needs hydrogen. What do we call something that needs hydrogen? It's a base, right? So it's going to become a base. So this one is going to become a base. So the acid, when it loses hydrogen, it becomes a base. But it's a special type of base that's called a conjugate base, right? And then same thing. Base needs hydrogen, right? But base gets hydrogen from acid. When base gets hydrogen from acid, now it has an excess hydrogen to give away. What we call something that has hydrogen to give away? It's an acid. So this is going to be a conjugate acid. All right. So in the end, you have, if you have an acid plus a base, the acid is going to give us a conjugate base. A base is going to give us a conjugate acid. Right? So a conjugate acid is what the base becomes after it accepts a proton. Conjugate base is going to be what the acid becomes after it donates its proton. Right? So this is the pair. It's a nice pair here. And by the way, it happens even when we have water. So we talked about how water behaves. So we talked about how, for example, let's say acid, right? This is an acid plus H2O that gives us H3O plus A minus. Look at this. HA is acting like an acid, right? We already know that. Acid. But after it's already given away the H plus, now it becomes a conjugate base. And H2O here, we already established that it acts as a base. Why? Because it accepts a hydrogen ion from the acid. So it acts as a base. But after it has received H3O plus, it's no longer a base. It's an acid. So it's a conjugate acid, right? So the acid will become a conjugate base, and then the base becomes a conjugate acid. And we call these acid-base conjugate pairs, right? So conjugate acid-base pairs and the acid and base on the opposite side of the equation, right? So these are what we call them. So whether it's water or something else, whenever you have an acid and base reaction, they're going to give you the conjugate acid and bases, always. All right. So that's pretty much the conjugate acid and base pair, and that's all you need to know. So in this question that we looked at earlier, B says that you need to identify the conjugate acid base pairs. All right. And all you need to do is, for example, this is acid, this is the base. This is the base. Those are the pairs. This is the acid, this is the base, right? Acid, base. This is a base that becomes a conjugate acid. So these are the pairs, and then the other pair is, this is a base, acid, base, acid, base, acid, and then this one, it will act as an acid and then base. So these are the pairs, right? These are the conjugate acid base pairs that we have in here. All right. So you should know now, if you have an acid base reaction, the acid and base conjugate. All right. So now let's talk about the dissociation of water. So we talked about how water is very special in that it can act as a base or an acid, right? So something interesting happens where, right, for example, if you have water here, you can have one water give a proton to the other water. So one is, the one that gave out a proton is acting as an acid. And the one that received the proton is acting as a base. So we call this ionization of water, or auto-ionization of water. So this is because the water is amphitrophic. Amphitrophic because it can act as a base and an acid at the same time. So this makes these ions very special. So if you were to calculate what we call the equilibrium constant, right? If you remember your equilibrium constant expression, calculating the equilibrium constant of this equation will give you an equation like this, because we usually don't include liquids and solids in our equilibrium constant expression. So we're going to have only the products in this one. So the KEQ is going to be equal to this. This is a very special KEQ. Why? Because the concentration in room temperature water, the concentration of H3O, right, and concentration of OH are going to be equal, and they are usually equal to 10 to the negative 7 molar. So they both equal to 10 to the negative 7. So the KEQ of water, that we call KW, is equal to 10 to the negative 7 times 10 to the negative 7 is equal to 10 to the negative 14 molar. And that has some implications that we'll talk about later today. But right now, you need to know that this is called the ion product of water, right? KW. So to recap, water dissolves in water pretty much. And what happens is that one water molecule gives away hydrogen, the other one receives it to get something like this, which it tells you that in water you always have H3O plus and OH minus. Another way you can think of it is H2O gives away H plus OH minus. This is the same way, it's just that H plus is never by itself, it's bound to water. So this gives us the concentration of H3O plus times the concentration of OH minus is equal to the 10 to the negative 14. Or another way, concentration of H plus concentration of OH minus is equal to 10 to the negative 14 at room temperature. And we will use these in the future, but this is the rule. This is an important rule. And let's talk about pH. Now, you've heard of pH before, and pH is important, especially when it comes to acids and bases, right? We talked about strong acids, strong bases, and you can measure the strength, but pH is it's a direct way to measure how strong they are, how strong or weak an acid or a base is. All right. So pH, what is pH? The pH is really, it measures the acidity or basicity of a solution. It goes from 0 to 14. All right. So let me look at it here. So pH really is, so it goes from 0 to 7 to 14. And if something is between 0 and 7, it's an acid. If something is between 7 and 14, it's a base. And if something is in the middle, it's neutral. That's the pH. And the formula for pH, right, is pH is equal to negative log of H plus concentration, right? Or just negative, so this negative here, negative log of H3O plus concentration. So these are all the same, right? H plus and H3O plus concentration are the same. H3O plus means H plus concentration in water. Now, going back to the scale here, acid, the strength of an acid increases as you go down the pH. So a very low pH means a very strong acid, right? So, for example, in the stomach, you have pH of 2. You have the strongest acids in the body. Now, a base is the opposite. It goes up this way. A base of pH 14 is a very strong base, right? So low pH means strong acid. High pH means strong base. All right, that's enough about that. So here, this is kind of how to give you an idea of how pH changes, right? So if the acid goes down as you if the acidity increases as the pH decreases, it means that if you increase the concentration of hydrogen, of H plus concentration, pH will go down, right? Now, another one. So we're going to build up the pH formulas as we go. So you have this formula that's really important. Another formula that's important is the one that we looked at earlier, where H plus concentration is equal to No, H plus concentration times OH minus concentration is equal to 10 to the negative 14. That's the pH. I mean, this is the formula that we use for pH. All right, so how do we measure pH? So usually you calculate pH by using known concentration of H plus or OH minus, because if you have any of these, you can just say, oh, pH is equal to the negative log of this. Or, if you have OH minus concentration, guess what you're going to do? You're going to use this formula right here, right? So let me show you. So if you have concentration of H plus times concentration of OH minus is equal to 10 to the negative 14, then the concentration of H plus is going to be equal to 10 to the negative 14 over concentration of OH minus. So if you have the concentration of OH minus, you can find the concentration of H plus. And if you found the concentration of H plus, you can find the pH, because we know that the pH is equal to the negative log of H plus concentration. Another important formula is something that we call POH. So pH is kind of like POH is kind of like pH, but in terms of OH. So it's equal to the negative log of OH minus. POH is really important because you can use it to find pH. How do you use it? pH plus POH are equal to 14. So now it's all coming together. All right. So I'm writing down the formulas for that we use to calculate pH. Here, also, if you want to calculate pH, you can, from this formula, find OH minus is equal to, well, 10 to the negative 14 over the concentration of H plus, right? Easy. So these formulas are used to calculate pH. So another really, really cool formula that we use is, what if I gave you pH? What if I gave you pH and I asked you to calculate H plus concentration? So sometimes you're given a pH, and then, so let's say pH is equal to negative log of H plus. How do you find H plus from here? Well, you use a bunch of algebra, but you end up with this formula that says that the concentration of H plus is equal to 10 to the negative pH. Ooh, I ran out of characters. Run out of space. Is equal to 10 to the negative pH. Maybe let me move this here. H plus concentration is equal to 10 to the negative pH. There you go. This is how you measure H plus when you're given pH, because sometimes they can give you that. Or, if you're given POH, it's the same idea. So POH is equal to negative log of OH minus. So from here, OH minus concentration is 10 to the negative POH. So by the way, this right here, we call it anti-log. So this is an anti-log of POH, right? So all of these are formulas that you can use to calculate your pH and, do a bunch of calculations around pH. All right. So let's see if I can find a good example that we can do. All right. So it says, what is the pH over 2.5 times 10 to the negative 4 molar HNO3 solution, right? So HNO3 is an acid, right? And HNO3 gives you H plus NO3 minus. You don't have to write down the equation, but this is showing you that the concentration of HNO3 is the same as the concentration of H plus. So this concentration that they gave you is the H plus concentration. So the concentration of H plus is equal to 2.5 times 10 to the negative 4 molar. All right, the concentration they already gave you. So what's the pH? The pH is equal to the negative log of the H plus concentration. And this is equal to negative log of 2.5 times 10 to the negative 4. All right. So you just do this in your calculator. Find the log of it. I think this should be about 3.6. Okay. So the pH here is 3.6. All right. Now, what if it's a base? What if it's a base? It's not an acid now, it's a base. Now, if it's a base, so they gave us KOH, right? If they gave you KOH, they gave you KOH, so they didn't give us the H plus concentration. If they gave you KOH, guess what they gave you? Because this is a strong base that gives you KOH, gives you K plus OH minus, then the concentration they gave you is KOH concentration. It's the OH concentration. So it's OH minus is equal to 1 times 10 to the negative 3 molar. That's the OH concentration. Well, how do you find the pH if you have the OH concentration? Remember our formulas. If you have OH concentration, H plus is going to be equal to 10 to the negative 14 over OH concentration. So here, that means that we can easily calculate it. So if you have OH, you can calculate H plus concentration is equal to 10 to the negative 14 over OH minus concentration. So this is equal to 10 to the negative 14 over 1 times 10 to the negative 3, and this is going to be equal to 1 times 10 to the negative 12 molar. That's the H plus concentration. And guess what? After you have the H plus concentration, you can easily find the pH. pH is going to be equal to the negative log Give me a minute. It's kind of stuck. What? All right. Let's get back. We're talking about calculating from a base, right? So all you need to do is just calculate the OH concentration. And then after you calculate the OH concentration, so now you already have the OH concentration. OH concentration, we have it. H plus concentration, we calculated from 10 to the negative 14 over OH minus concentration. And then pH, we calculated from negative log of H plus. Pretty easy, pretty straightforward. All right. So let's find another one. What about calculating H plus or H3O plus concentration from pH? So we already looked at the formula for this, right? So we saw that if pH is equal to negative log of H plus, then H plus is equal to 10 to the negative pH. And that is all you need to do. Right? By the way, remember that the concentration of H plus is the same as concentration of H3O plus. So don't get confused by that. So all you have to do is just say H plus is equal to 10 to the negative 4. That is it. That's all you need to do. Calculate H3O from pH. All right, let's look at another example. What about calculating OH minus from pH? So there are different ways to do this. So let me use my. So there are two ways. Let me show you the easy way. The easy way is this, right? So we know that pH plus POH is equal to 14. So POH is equal to 14 minus pH. So POH is equal to 14 minus pH, in this case is 4.95, right? So this should be equal to 9.05. That's the pOH, not the pH. pOH. All right. Now, if you have the pOH, how do you find the OH minus concentration? Remember that pOH is equal to negative log of OH minus, but this gives us concentration of OH minus is equal to 10 to the negative pOH, right? So all we have to do is just say OH minus is equal to 10 to the negative 9.04. And you just do this in your calculator. That's the pOH concentration. That's one way to do it. Another way is you can, from the pH, you can find the concentration of H plus from the pH, which is 10 to the negative pH, like this. And then from there, you can find the OH concentration by saying that it's equal to 10 to the negative 14 over H plus concentration. Right? So there are many ways to do it when you have all the formulas. So it should be pretty straightforward and it should be pretty easy to do. All right. So that's enough examples on the calculations of pH. So the pH scale is pretty broad, right? So you go from 0 to 14. Again, strong acids like HCl will be at 0. You have lemon juice at 2, stomach acid as at 1, vinegar as 3. So they are all acids. Coffee is a little bit acidic, tomatoes, saliva is a little bit acidic. And then in the middle, you have 7, which is pure distilled water. Pure distilled water is 7, it's neutral. Your blood is about 7.4. And then baking soda is basic. Oven cleaner is basic and things like that. NaOH is a very strong base. So one last thing that I'll talk about pH is that when you change one pH, because it's a logarithmic scale means that pH 1 versus pH 2, pH 2 is not just twice as much, it's 10 times, because it's a logarithmic scale. One more number means 10 times. The next number means 10 times more. So that means that, to go from one pH to another, it's a huge change. It's a big difference, right? So if each tenfold change changes the pH unit by just 1, right? So you need to understand it in that way. That's why, for example, if the pH of your blood drops even by 0.2, you get sick, right? So that's why we need to maintain pH very, very, very steadily in your body, and we'll talk about it about how we do that. So a few areas where we need pH, for example, in agriculture, you have to monitor the pH of the soil. In physiology, in the body, you gotta monitor the pH of the blood. Acid rain is a big problem because it's acidic and it lowers the pH, and fish and soil suffer because of that. Sewage system and water and all that stuff, you need to use proper pH. And in industry, we also use a lot of pH measurements. All right, so I think that's enough about pH, and let's talk more about some reactions involving acids and bases. So let's talk about neutralization and titration. So neutralization comes from the fact that when you add an acid and base together, they neutralize each other. So when you take a strong acid, for example, HCl, plus NaOH, a base, they're going to give you a salt and water. So Na is going to bind to Cl, NaCl, H is going to bind to OH, so it's NaCl plus water. This is a neutralization reaction, right? It's very, very common. So the neutralization reaction of water is what we call, it's a neutralization reaction, and we use it. So the net neutralization really is talking about you take H plus ions plus O minus ions, you give water. So a strong acid plus a strong base will give you salt and water. Why are we saying this? This is important because it's important in what we call titration, right? So let me go back here a little bit. So you have an acid, right? Strong acid, strong base, and they give you salt and water. This is neutralization. That's why, by the way, we call it neutralization, because it goes from a very high pH and a very low pH, and then you get salt and water, which are neutral. The pH is neutral. So strong acid, an example is HCl, strong base NaOH. So you add this together, you get salt NaCl, then water H2O. All right, pretty cool. Now you can use this, right, to neutralize an acid, or you neutralize a base. So if you have a acid here, you can add a base to neutralize it. So you have an acid here, you have a base here, you can add them, and the solution that you're going to have is going to be, in the end, salt and water. So I want you to notice one thing here. Remember stoichiometry. So 1 mole of HCl bound to 1 mole of NaOH to give us 1 mole of NaCl and 1 mole of water. And this is a balanced reaction. So from here, you can actually calculate concentration of an unknown acid or base. How do we do that? We call this titration. So in titration, you start with a flask at the bottom, right? Make sure you can see it pretty well. You start with a flask at the bottom, and then the flask contains an unknown concentration of a base or acid. And then here at the top, we have something we call a burette. And what do we use it? We're going to add a known concentration until they have both reacted. So, for example, we can add a known concentration of, we can have an unknown concentration of HCl, and then a known concentration of NaOH, and then we start with HCl here, unknown. We add a known concentration of NaOH, but in the end, we're going to neutralize this, right? We're going to neutralize this. Even though we don't know the concentration of this, we're going to neutralize it. And we have things that we call indicators to tell whether or not we reached the neutral point. We call this the equivalence point. So if you meet the neutral point, the equivalence point, it means that the number of moles of HCl added are equal to the number of moles of NaOH added. Because we neutralized everything. We at pH 7. We don't have an acid or a base in the solution anymore. We've made salt and water. All right. So let me show you how it looks like in the lab. I think I can do that. Let me see if we have that. There you go. This is me doing a titration in the lab. So up at the top, I have a known base. At the bottom, I know I have an unknown acid, and I'm adding little by little until I reach the point of equivalence. How do I know? It's because I've added an indicator in the beaker at the bottom, and an indicator changes color when we reach equilibrium. So notice that I'm getting closer to it. I'm getting closer to it. You see the change in color, and then boom, it goes away. So you gotta wait until the color doesn't go away, and there you go. We reached equilibrium, right? So there we have a neutral solution, and the neutral solution is going to help you calculate the concentration of the unknown acid, and I'll show you how. And the main thing that you need to know is that at equivalence point, the moles of acid and moles of base are equal, right? And we use an indicator. So this is an example of an indicator. This is the video from the video that I just showed you here, where it changes color when you reach the equivalent point, right? So you place a known volume of acid. So the volume is known, but the concentration is not known. And then you add an indicator, and then you use a known concentration of NaOH in a burette. So now you know how a burette looks like, and then you add NaOH. So that's the titration part. Why is titration important? Titration is important because if you titrated, so let me draw this again. So you have your nice burette right there. You have your acid at the bottom, right? So the acid, and then here you have the base in the burette. And look at this. In the end, you're gonna know the concentration of the base. We know the concentration of the base, so let's just call it Ma. M stands for molarity. MB. The concentration of the base is MB. You will know it because it's a known concentration. The volume of the base added, you will know it because you will take a reading of the burette at the beginning and the end of the titration. So the volume of the base added, you will know. And then what about the acid? The volume of the acid we know because, well, that's what we started with. The concentration of the acid is what we're looking for, because remember, it all started with an unknown concentration of acid, right? So if only there was a way to combine all of this. There is. It's MaVa is equal to MbVb. That's how you solve for this, right? And also you have this, well, we have all of this. How do we solve for Ma? You just divide both sides here by what's next to Ma. So let's solve for Ma from our equation. So solving for Ma is to divide both sides by what's next to Ma so that they cancel out. And Ma is equal to MbVb over Va. So you can calculate the concentration of the acid given this, and that is right here, the formula that we're going to be using. So this formula is the crucial formula for titration, because we have everything except one. Now you might be wondering where this formula comes from. This formula comes from the fact that at equilibrium, the number of moles, so the number of moles, let's call it N, the number of moles of acid will be equal to the number of moles of base at equivalence point. We know that. Well, remember, molarity is equal to the number of moles over volume. If we move this around, the number of moles is going to be equal to the molarity times what? Times volume, right? So because of that, that's what we're doing. The number of moles of the acid is going to be equal to the molarity of the acid times volume of the acid. The number of moles of base is going to be equal to the molarity of base times molarity of volume of base. So that's where it comes from. But this is what you need in terms of titration. So let me give you an example. Here, calculate the acid concentration, right? If everything else is given to you, calculate the acid concentration. And then, so you have the volume of HCl, the volume of NaOH added, the concentration of NaOH because we know it. Well, all you need to do is, again, we have the formula. Let's see if you can see this. Let me write it up here. All right, so the formula is MAVA is equal to MBVB. And then here we're wanting the concentration of the acid, so MA is equal to MBVB over VA. All right, so MB is the concentration of the base. The concentration of the base is 0.1 molar. VB is the volume of the base added, 35 ml, over VA, which is the volume of the acid, 25 ml. So 0.1 times 35 over 25 is 0.14 molar. So the concentration of the acid, the one that we were looking for, or MA, is 0.14 molar. Beautiful. You can do that from titration. Now, I can also ask you to calculate the concentration of NaOH. So now I just switched it up. I'm asking you the concentration of NaOH. If 25 ml of this solution, so it's asking you the concentration, so it's asking you MB. If 25 ml of this solution, so the 25 ml of the NaOH is volume of the base, 25 ml, we're required to neutralize 45 ml of 0.3 molar HCl. So the volume of the acid is 45 ml, and then the molarity of the acid, the concentration, is 0.3. Well, how do we find MB? MAVA is equal to MBVB. Let's solve for MV. MB, how do you solve for MB? Divide both sides by what's next to MB. This case is VB, so that this can cancel out. So MB is equal to MAVA over VB, and then you just substitute. MA is concentration of the acid, VA is volume of the acid over VB, the volume of the base, 25 ml. So 0.3 times 45 over 25. .54. So I got 0.54 molar as the concentration of the base, right? So it's just when it comes to titration, you just remember the equation MAVA equals MBVB. That's all you need to remember, and you will know the calculations. So that's about it when it comes to neutralization and titration, and make sure that you know how to calculate all of these. Now, let's talk about polyprotic acids. What are these? Notice poly in the name. It just means that these are acids that have more than one hydrogen, right? So the acids that we've been looking at have a 1-to-1 ratio of acid and base pairs. Polyprotic acids donates or accepts more than one proton. A polyprotic substance will donate more than one proton per formula unit, right? So the other ones that we've been looking at are monoprotic acid, but sulfuric acid, for example, is H2SO4. It's diprotic acid. And the only thing that's different is now that it has two hydrogen ions, when it binds with NaOH, it's going to need two on NaOH, right? Because it's going to give two hydrogen ions. So, for example, let's look at how they react in water. So it's pretty much the same thing, but you have more than one hydrogen. So you have, for example, H2SO4 in water is going to be, usually it's H3O plus, but water will have just taken one hydrogen, but we have two. So what we're gonna do, we need two waters, then two of these, then you have SO4 2 minus. That's all you need to know about polyprotic acids. We can talk more about those, but you have another example is H3PO4. Obviously this one will give you three hydrogens, but these act very differently, but we won't get into details about what they do. It's just that know that some acids gave away more than one hydrogen, and some bases accept more than one hydrogens, and these are called polyprotic acids and bases. All right. Now let's talk about buffers. Buffers are really cool. Why? Because buffers are solutions that resist changes in pH. So it's a solution that you have, and you add an acid, doesn't change pH. You add a base, it doesn't change pH. It resists to changes in pH as much as it can. And these buffers are really important in the lab and in the body, because think about it. If you eat something that has high acid, it can change the pH of your blood very, very quickly. But your body and your blood has a buffer system that will resist to the changes in the pH, right? So that's why here I have where you have laboratories, you have your body, you have commercial products, and all these other places, you need buffer solutions. So how do they do that? Buffers establish an equilibrium between a conjugate acid and base pair. So buffers are made by an acid and base reaction, right? But it's very important to know that buffers are made of either a weak acid and its conjugate or a weak base and its conjugate. So it has to be weak, it can't be strong. Weak acid and its conjugate or a weak base and its conjugate. Very, very important to remember. All right, so let me give you an example. So a buffer is going to be kind of like your normal acid, right? So you have your acid behaves this way. HA gives you H plus plus A minus. So a buffer system is a system that's going to have both this acid and its conjugate base. That's a buffer system. And it's going to have to be a weak acid. So this is a weak acid. This is a conjugate base. So a solution that has both of these will be a buffer system. If you have a base, so a base, we know that a base gains hydrogen ion to give you BH plus, and this is a weak base that gives you a conjugate acid. A buffer system will be a system that has this base and this acid, this conjugate acid. So this is an acid buffer system. This is a basic buffer system. Now, let me give you an example. An example of a weak acid that we already looked at is CH3COOH gives you H plus plus CH3COO minus. So right here, if you have a system that has CH3COOH, acetic acid, and then this ion right here, it's going to be a buffer. What about here? If you have a weak base that we talked about is NH3. So if you take NH3 plus H plus gives you NH4 plus, it's going to be a buffer system, right? So it's going to be a buffer system that has NH3 and NH4 plus. This is what a buffer is. Weak acid and its conjugate, or a weak base and its conjugate. It's a pair, right? Now, one thing that you will see that confuses people is that usually we don't store NH4 plus. So NH4 plus is usually not by itself, so it might be NH4Cl, like that, right? Or CH3CO minus, it might be CH3COO bound to sodium. It's still a buffer system. So let's see if I have examples here. Yeah, so I have an example of a buffer system that has acetic acid and sodium acetate. So this acetate here has an acetate ion. So this is a buffer system. All right. So something interesting happens, and this is what we call these buffers. So if you have an acid buffer system, HA plus, not plus, HA gives away H plus, and you have A minus. If you have this system and you have these two things in a solution, this is how a buffer works. If you add an acid in solution, right? Acid has H plus, right? Remember, if you add an acid in solution, guess what's going to happen? The base is going to take care of it. The base is going to neutralize it. If you have a base in solution, guess what happens? The acid is going to take care of it. So that's why there are buffers. Adding a basic substance to a buffer causes changes. Adding a basic substance to a buffer is going to really just make it so that the acid takes care of it. And if you add an acidic substance to a buffer, the base will take care of it. All right? So that's pretty much how a buffer works. You have two entities. You have an acid entity and a basic entity. And the acid will take care of the base, and the base will take care of any added acid. That's how we resist changes to the pH when we have a buffer. But it doesn't work completely. It's not like perfect. So we have something called a buffer capacity, right? So it's a measure of the ability of a solution to resist large changes. So if you have a high buffer capacity, then our buffer will resist the pH. It will resist changes to the pH. But if you have a low buffer capacity, you will add a base or an acid and it's going to change just like that. So it depends on what buffer. All right. So that's pretty much what a buffer is. Now, how do we prepare buffers in solution? All you do is, you get two things. So a buffer, you need two things in solution. So for example, if you're preparing an acid buffer, you're going to have a solution of your acid and a solution of your conjugate base, and then you put them together. But knowing how much that you're going to put them together depends on the pH. So let's talk about the pH of a buffer, because the pH of a buffer capacity is kind of neat, kind of very interesting. So if you have an acid like this, right? If you have an acid like this, the equilibrium constant, you have to find the equilibrium constant. The equilibrium constant of the acid, we call it Ka, or we call it the dissociating constant of the acid. And most of the acids will give you this number because it's a constant. Most of the acid, you'll be able to look up this number, or you will be given this number in the problem. So if you have the Ka, you can calculate the pH of a buffer system. So pH of a buffer. pH is equal to pKa plus log of concentration of A minus over concentration of HA. And we know this, right? We know this from the equation. HA gives you H plus A minus. So H plus is the acid, A minus is the conjugate base, right? So pH of a buffer is going to be equal to pKa plus log of A minus over HA, and these are concentration. What's pKa? pKa is equal to negative log of Ka. So if I give you the Ka and you know the concentrations, you can find the pH. You should be able to find the pH, no problem. Let me see if I can find an example, actually. Should be able to find a good example when it comes to buffers. Oh yeah. Let me see. There you go. Should be able to see it. All right. First of all, how can a buffer system resist changes in pH upon addition of a strong acid? Well, if you added a strong acid, what's going to happen? Wait, where did it go? So if you add a strong acid to a buffer system, it's going to be taken up and neutralized. Neutralized by what? It's going to be neutralized by the base. So this is the base in our system. So this is the acid in the system. This is the conjugate base. So if you add a strong acid, it's going to be neutralized by this base. So the reaction is pretty much going to go this way. That's what's going to happen. So another question is, which of the following should be mixed with hydrofluoric acid in order to make a buffer solution? It's a good question. So remember that a buffer solution, so HF is a weak base, right? So if you have now a weak acid, so if you have a weak acid, HF, to make a buffer, it will be something that has F minus in it. So what has F minus in it in here? It's B. B has F minus in it. So that's, NaF and HF will make a good buffer solution. All right. Now it says a buffer solution is prepared in such a way that the concentration of this and the concentration of these are, they gave you the two concentrations. And then they're asking you the pH, and they gave you the equilibrium constant, right? So they pretty much gave you these two things, right? Look at this. They gave you this equation right here. And then they gave you this equation. So this is pretty much what we've been looking at. This is a weak acid, HA plus H2O gives you H3O plus A minus. So this is our A minus. This is our HA. And they gave us the concentrations for those. They told us that 2 times 10 to the negative 1 is pretty much 0.2 molar. And then here A minus is 0.1 molar. So they gave you the concentrations and they asked you for the pH, and this is the Ka. The Ka is 1.34 times 10 to the negative 5. How do you find the pH? Well, the pH equation. pH is equal to the pKa plus log of A minus over HA. Wow, and look at that. You have A minus here. You have A minus concentration is here. You have HA concentration is here. And then pKa is what? pKa is equal to negative log of Ka. So you have the Ka. You have the Ka here. So negative log of Ka gives you the pKa. Then you have A minus and HA, and it's just a matter of substituting and putting it into the calculator. So that's how you find the pH of a buffer system. All right. And that should be enough really about the pH, about the buffer systems, about the acids and bases. I think we've talked enough about it, and you should be able to answer any of those questions. If you want, if something is not clear, you can rewind this video. You can go back and do more practice. Make sure that you write down those formulas that I've given you throughout this video, because I need you guys to know this so that you can answer the questions in the quizzes and the exams correctly. All right, see you next time.